Thank you. Okay, so let me start by expressing my gratitude to the organizers of the summer school and all the members of the scientific committee of the program for for having me here at the Fields Institute. I will keep great memories of my week in Toronto. And also, on a more personal level, let me thank Robert and Chao for their help, cooperation, and patience in dealing with more than 30 problems I had prepared for the summer school. Okay. So today, I would like to sort of close the circle and go back to the Euclidean scenario where we started from with the Bernstein problem and sort of ask similar questions to the ones we asked yesterday in the tree-sphere with the round matrix. So we wonder about classification results. And I want to give you several perspectives on contemporary research in the field. So this is lecture 5. And the title is Beyond the Bernstein Problem. Okay. So if you remember, the Bernstein problem was the following. We were considering maps, say in C1, from Rn to R, okay, solving the minimal surface equation, so solving the following quasi-linear elliptic problem. And the conjecture, which is motivated by what we discussed in the first lecture, is that indeed the only solutions to this problem should be affine functions. But I also mentioned the fact that somehow this is only true when n, so this is only true. So we have only affine solutions, which is what Bernstein had conjectured if and only if n, so the number of variables, is less or equal than 7. Okay, otherwise the conclusion is false. And so I guess the first thing I want to do today is to prove this theorem when n equals 2, which is a lot simpler than higher dimension, but still contains some interesting ideas. So what I would like to call Theorem One today is to prove that the Bernstein conjecture is true if n equals 2. And so to do that, we need to recall something we had proven. So we proved that modulo a set of L1 measure 0 of radii, then an entire minimal graph is area minimizing, and it has quadratic area growth. So we can certainly find a sequence Rk, which is in fact conveniently taken to be a set of dyadic powers of a given real number ρ. So here k is greater or equal than 1, say, such that the graph of the function u, so the solution of the minimal surface equation we are considering, intersected b, so the Euclidean ball centered at the origin and of radius Rk, is area minimizing. In the sense that we discussed in the first lecture. So somehow, a priori, we can only consider competitors that are in the cylinder above the basis that we are considering. And so this assertion has two implications. The first one is that gamma u is stable which means that for any f in, well, let's say C1 compactly supported, we do have the stability inequality. That is to say that the integral over gamma u of a square f square is less or equal than the integral over gamma u of grad gamma u square. Oops. Okay, this is obviously an f. Okay. And the second implication is that, like I was mentioning, is that we can compare with spheres, and so we have quadratic area graph, like the area of gamma u intersected b centered at the origin and of radius rk is less or equal than this universal constant, which is just 2 pi times rk square, and this is true for any k greater or equal than 1. Okay. And so how does the proof work? So the proof is based on a very simple idea, which takes a little bit of effort to be implemented. So the idea is just, let's take the stability inequality and set f equals 1, right? So if we set f equals 1, then the right-hand side is 0. So that, and the left-hand side here would be the integral of a square. So we would conclude that the integral of a square is equal to 0, which means that a, so the second fundamental form should be identically equal to 0 at each point, which means that gamma of u is a totally geodesic submanifold, therefore a plane. What is the problem? Well, the problem is that somehow f equals 1 is not an allowed competitor, right? So, a priori, the notion of stability we want to use, which turns out to be the right one, is just that we want to take f to be, say, C1 compactly supported. And in fact, of course, by an approximation argument, one can actually take f in W1 to gamma u r. Okay, but certainly the constant 1 does not live here. Okay, and so what we are going to do is an approximation argument, which is known as logarithmic cutoff trick, which is a typical two-dimensional So how does it work? Well, I'll start by giving you a fake proof, which contains the idea, but somehow, and the simplest way to implement it, but doesn't quite work unless you make an extra assumption. Then I will tell you how to modify it to get an actual proof. So let me start with a fake proof, which is still quite enlightening. So the fake proof is the following. We have this sequence of radii, and we take the function f rho, or let's see, right, f rho, which is a function defined in the ambient, so a function from R3 to R, which is defined as follows. So f rho is equal to 1 inside the ambient ball of radius rho, is equal to 0 in the complement of the ball centered at the origin and of radius rho square, and interpolates logarithmically between the two, in between. So that's, you need to take 2 minus log r, where r is just the distance from the origin in R3, over log rho in the annulus. Okay, so let me call it A rho square, the annulus in between. Okay, and then then what we are going to do is that we are going to so then we restrict this function, which is defined in R3, to the graph, and we specialize and then pick. So we specialize the radius rho to be equal to Rk. That is to say, we want to take rho to be equal to rho to the 2 to the k for some k. Okay, in fact, for any sufficiently large k. Okay, so that's a function in W1, 2 when you restrict it to the graph. So it's a legitimate competitor in the stability inequality. So we just need to make an estimate on the Dirichlet integral. So we want to make now an estimate on the integral over gamma u of the tangential gradient of f rho k square. Okay. So it's pretty clear that the only contribution you have is in the annulus, because the function is constant everywhere else. And so in that region you will have the ambient gradient of f rho is equal, well, we only have the contribution there, and is equal to minus 1 over log rho times 1 over r. And so it's pretty clear. So let me maybe draw a picture. Let's say that this is R2 inside R3. So here we have our graph. And we take the annular region between red and blue. Okay, that's enough. And we do have an energy contribution in this region here. So I claim that this integral here is certainly bounded from above by the integral between 1 and rho square of 1 over log rho square times 1 over r square dr. Let's see, I would have 1 over rho square r dr, okay? I'm integrating in polar coordinates in R2. So I'm now using the coordinates on R2 to perform the integration. And so, okay, so what is the value of this integral? Well, this is equal to, I get this 1 over log rho square times the integral of 1 over, so dr times 1 over r, so I get log, so this is certainly bounded, say, by log rho square, which is 2 log rho. And so this is equivalent 1 over log rho. And so now I will pick rho equal to rho to the raised to the power 2 to the k. So now we pick rho equal to rho to the power 2 to the k, and let k go to infinity. And this says that the integral over gamma u of a square f rho k square is less or equal than the integral over gamma u of grad gamma f rho k square. As we let k go to infinity, this guy goes to 0 by the argument above. This guy will converge monotonically to the integral over gamma u of a square. Okay, so the conclusion is that this guy will go to 0 as well. Okay, and this is only possible if a square is identical to 0, which means that the graph is an affine subvariety. So A of, U of xy will be equal to AX plus BY plus C for real constants A, B, and C. Okay. So why is this a fake proof? What is the problem here? Well, the point is that, maybe let me write it here. So the remark is that, like I wrote it here, this is okay only if I knew a priori a gradient bound. Why is that? Well, the point is that what I'm implicitly doing here in this step is that I'm integrating over the yellow region downstairs. Now, if you want to apply the area formula in the correct way, then somehow the volume element, so the volume element here on the graph would be equal to 1 plus grad U square times the two-dimensional Lebesgue measure. So when I write the area element like a constant times RdR, well, that's okay if I know well, it's okay modulo constant if I know that the gradient is bounded, okay? Because in that case, the measure on the graph here, the volume element will be comparable to the Lebesgue measure. But if the gradient is not bounded, then unfortunately, this step is not legitimate, okay? Because I may have an extra factor, in fact, this factor here, which creates problems. But now I claim that there's a tiny modification of the proof that doesn't really need this assumption. And so let me tell you about such modification. So the point is simply the following. So the proof, let's say, okay, is the following. So let's now assume for simplicity that we can take radii of the form e to the k for k greater or equal than some k naught. And we consider the function f of n, which is equal to 1 in the ball centered at the origin and having radius e to the n, equal to 0 outside of the ball of center 0 and radius 2 to the n, and is logarithmically interpolating in between, so that would be 2 minus log r divided by n in the annulus between e to the n and e to the 2n. So far, this is actually what I was doing before. Doesn't seem to be any change. But now, the point is that I want to compute the integral doing some sort of dyadic decomposition. So what I will do is that there is this for any n, I have this large interval between e to the n and e to the 2n. So now I decompose it in the following way. So I'll start with e to the n, then I take e to the n plus 1, e to the n plus 2, and so on and so forth. So I get n intervals here. And so, well, now let's do the estimate for the energy term. So this will be controlled by the sum for, say, I between n, so let's say L between n and 2n minus 1 of the integral on the graph intersected with a ball of radius e to the L plus 1 minus the ball centered at the origin and having radius e to the L of the same thing. And now, well, the estimate for the gradient is the same, so I get that this is controlled by the sum for L between n and 2n minus 1. And so let's see. So here I will get, so the contribution is only in the angular region. I get something like, let's see, I get 1 over n squared. And then it's, I can bound the derivative of the log with something like 1 over e to the 2L. And then the area, well, the area can just be bounded, the area of the corresponding dyadic integral in R3 can just be bounded by e to the 2L plus 1. So I just replace the annulus with the whole large ball. And so here, this is nothing but the sum for L between n and 2n minus 1. And so I get 1 over n squared times e squared. Okay, and this is, well, I have n sum-n's of this form, so this is equivalent to e squared divided by n. So as I let n go to infinity, this will go to 0. Okay? And so, well, I'm saying that the energy terms along this test function will go to 0. The stability inequality will then give me the opportunity to finish the proof in this way here, right? Because any n, I have the inequality for the function fn. So the right-hand side goes to 0 as I let n go to infinity. So the left-hand side must also go to 0. Therefore, a squared must be identically equal to 0. Therefore, the function is a function. Okay, so somehow the logarithmic cutoff trick is the key idea to employ, but if we don't have an a priori gradient bound, we need a slightly smarter idea to estimate the integral. Okay, so that was the proof of Bernstein in dimension 2, and then we wanna go on the next step. So what is the next step? Well, the point is that a graph is a very reasonable object from the perspective of analysis, but not quite from the perspective of geometry. So the general principle that I learned from my advisor is that, geometers don't really want to use coordinates. When you use coordinates, you should feel dirty, right? And so we want to ask the same question without using coordinates. So what is the right way of asking the same question without using coordinates? So the question is the following. Let's see. So we want to ask, what are all, say, properly embedded complete, so no boundary, stable, minimal hypersurfaces in, well, let's say sigma n inside Rn plus 1. So this is somehow, well, we have already seen that a graph is stable, okay, because it's area minimizing in the sense that we described. So we can just extract that property, stability, and ask the same question without mentioning graphs. And so, well, again, by induction, somehow people expect the only such guys to be affine, right? That's what is reasonable to expect. And so, what is the answer to this question? So the answer is that if n equals 2, so if we are in R3, then the expectation is correct. So you get only affine functions. And this was proven between the late 70s and the early 80s by 3 groups of people. So there's one proof by Doccarmo and Peng, one proof by Fisher-Colbury, and Shane, and another proof which was published, I guess, a little bit later by Pogorelov, which is in fact the one that I will discuss here. Okay, so we do understand the situation for n equals 2, and so maybe you would expect that as we do in the Bernstein problem, then we can answer the question for any n, but there's bad news that even for n equals 3, I would say that we really have no clue. So if you take this question and add some words, like polynomial volume growth, then we do have a proof. But if you take it as it stands there, we really don't know. I mean, it's of course conjecture that it should only be affine hyperplanes, but we don't know. So what I would like to tell you now is how to prove this result for n equals 2, and there are various proofs. I will go with I will give a proof which is very close to the one given by Pogorelov, I guess, in 1987. So the general idea, which I may write here, is essentially the following. We want to do, again, a logarithmic cutoff trick, but we don't want to do it extrinsically, so with a function defined on R3, and with the area growth, which is extrinsic, so again in R3, but we want to do it intrinsically on sigma. So the key point here is to prove that stable implies intrinsic quadratic area growth. Which is what I will state now precisely. So when you gain quadratic area growth, then you will again apply a logarithmic cutoff trick, essentially with the same function, but defined now intrinsically on sigma. So let's see it. So first of all, let me maybe state this idea in a slightly more precise fashion. So the statement is essentially the following. So this is really the key lemma in proving that rigidity theorem. So the lemma is that if you have again, let's say, we take a ball on a surface sigma, and so when I use this notation, I really mean the set of points. Let's say we fix a center x, and we look at the set of points on sigma whose geodesic distance on sigma is less or equal than r0. So let's assume that such ball is stable, simply connected, so it's a disk, and two-sided. So, I mean, if you have a graph, like we were discussing before, two-sided is automatic, but in general it's not. So then we do have, quadratic area growth intrinsically. That is to say that the area of the ball in question is less or equal than 4 pi over 3 times r naught square. So just to get a feeling for this result, you should remember that when we take a flat plane, sigma were flat, if we take a disk on a flat plane, then here we would get a constant pi. So I'm just saying that modulo replacing pi with a slightly larger number, 4 pi over 3, then actually the conclusion is true for any stable minimal disk. Okay? So the proof of this fact is sort of elementary but quite clever. So let me outline it. Well, in fact, I will give it in detail. So the first step is to check the following two identities. So the first one is that the length of the boundary of the ball in question, so remember that sigma is a two-dimensional object, so this is really a curve. So the length of this boundary minus the corresponding Euclidean length, which would be 2 pi times r naught, can be expressed like in the following fashion. So like minus the integral between 0 and r naught of the integral on b rho sigma x of the Gauss curvature. And the second identity, which is gotten just by integration from the first, is, and I will prove the first in a second, is that in fact the area minus the corresponding Euclidean area as a defect, which is expressed by a triple integral, which is the integral between 0 and r naught of the integral between 0 and tau of the integral between b over b sigma rho x of k sigma. So how do you prove the first? Okay, they look super ugly, I understand, but let's prove the first one and convince ourselves that it's in fact very easy. So the proof of this one goes as follows. So let's take the first variation formula in dimension 1. So let's take the first variation formula. So that takes the following form. d dt of the integral over the boundary of the ball centered at x and having radius, say, let's see the letter that I want to use. Well, let's say that I want to, let's say that I call this letter t, and let's integrate the function 1. So we take the variation of the length, so the variation of the one-dimensional measure is equal to the integral of the mean curvature over the same ball, right? But the mean curvature in dimension 1, so the second fundamental form is just a 1-by-1 matrix whose only element is the geodesic curvature of the curve in question, right? And so now we can use Gauss-Bonnet because we are assuming that the domain is simply connected. So this is a disk, so we get 2 pi minus the integral over the ball on sigma having radius t and centered at x of the Gauss curvature of sigma. Okay, and now we take this identity and we integrate. So now at this stage you integrate, between for t between 0 and r naught, this identity in dt. So here we will get the length of the boundary at r naught minus the length of the boundary at 0, which is 0, equal to 2 pi times r naught minus the integral between 0 and r naught of the integral of the Gauss curvature. So that gives the first identity. And then the second identity comes just by integrating once more. Okay, so if you integrate this term, you get from the boundary length you can gain this identity for any r less or equal than r naught. Okay, so if you integrate in dr, you get the area of the ball here, you get pi r naught square, and you get a triple integral there. So once you get there, we are almost done, because we just need to integrate by parts. So now, we take the second identity and recall that for a minimal surface, the Gauss curvature is nothing but minus the second fundamental form square over 2. So if we plug in the second one, we get that the area of the ball we are trying to estimate minus the corresponding Euclidean area is equal to, well, I have minus times minus is a plus. I get 1/2 the integral between 0 and r naught of the integral between 0 and tau of the integral over the ball centered at x and having radius rho of a square. And now I integrate by parts. So now we integrate by parts twice. So we use the following. We use that the integral between 0 and r naught of f double 2, so let's say f of t g double prime t dt is equal to the integral between 0 and r naught. Now I will tell you about the choice of f and g. But the integral, I can move two derivatives on f with the following choice. So we take f of t to be equal to, let's see, the integral between 0 and t of the integral over the ball of radius rho and centered at x of a square. So that's the integral I have here. So that would be my choice of f. And then as gt, I just take 1/2 r naught minus t square. Okay, and I claim that if you perform the integration twice, all boundary terms will vanish. Okay, it's just a reality check. Okay, and when you move two derivatives from g to f, okay, you will kill the outer integrals. So you will only get so when you take two derivatives, you will get just the integral on dB t sigma x of a square. And so now you're integrating in dt over a boundary, so you get just the integral over the ball, okay? And so I claim that if you integrate by parts twice from here, you will actually get 1/4 integral over between, say, 0 and r naught of, let's see, you get the integral on the ball on sigma of radius r naught and centered at x. And here we will get a square times r naught minus r square. And so once you get here, we are almost done, because now we just need to apply the stability inequality at this level. So this will be less or equal than 1. So this is by stability. This is less or equal than 1/4 the integral over the ball of the gradient of the function r naught minus r. Okay, but the gradient of that function is less or equal than 1, so I just get the integral over the ball in question of 1. So I get 1/4 the integral over, I just get 1/4 the measure of the ball in question. And so now I compare the beginning with the end. So I get, if I multiply by 4, so what I'm doing is that I'm taking the leftmost terms and the rightmost term here. So I multiply by 4. So if I multiply by 4, I get, so let me maybe make a box here to conclude. I get 4 times the measure of the ball minus 4 pi r0 square is less or equal than 1 times the measure of the ball. So now I rearrange, I get 3 times the measure of the ball less or equal than 4 pi r0 square, okay, which is what I wanted to prove. And so how does the proof go? How does the proof go now? Well, once you get quadratic area growth, I claim that you can just take these test functions, but now you don't want to work extrinsically in R3 and restrict, but just work intrinsically on balls and annuli on sigma, okay? And so the whole proof goes on in a similar fashion, modulo the fact that for this estimate to be true, you need to know a priori that your surface sigma is simply connected, right? So we have, so this estimate here needs that your domain, the domain that you want to use, be simply connected. And so here there's a technical point. So if you know a priori that sigma is simply connected, then you can just complete the proof of that theorem by the logarithmic cutoff trick, as I explained. If not, if you don't know a priori, then you need a couple of tricks. And so let me just mention them. So a priori, sigma is not or may not be simply connected. But there's a standard way out. So if this is sigma, and I call, I don't know, phi, the embedding of sigma into R3, I can just take the universal cover of sigma, which I may call sigma tilde. So let sigma tilde, let me call pi the projection. So let sigma tilde comma pi be the universal cover. And so this universal cover naturally comes with a stable minimal immersion, which I may call phi tilde. So it comes with a phi tilde from sigma tilde into R3, not necessarily an embedding, but certainly a stable minimal immersion. And in particular, at each point, we know that k sigma is equal to minus a squared over 2, less or equal than 0. So this is also true. So it's also true that when we pull back on sigma tilde, this is also less or equal than 0 at each point. So in particular, by Cartana-Damar, sigma tilde is diffeomorphic to R2. So in fact, the exponential map from the tangent space at any given point to sigma tilde, which is isomorphic to R2 into sigma tilde, this is a global diffeomorphism. Okay? And so in particular, sigma tilde is just a copy of R2, and now I just perform the logarithmic cutoff trick intrinsically on sigma. So this area bound is intrinsic, and I just pull back all structures to sigma tilde I apply the stability inequality there, so that's just a function inequality that happens on sigma tilde. And so now, at this level, once you gain this, now just do the logarithmic cutoff trick. On sigma tilde. And the proof is really identical to the one of Bernstein that I gave before. So again, if you don't like this technical point, you can still prove the theorem when sigma is non a priori to be simply connected. Otherwise, you just need to go from embedding to immersions because you need to pass to the universal cover and use Cartan-Adamar to make sure that your sigma tilde is diffeomorphic to R2. Yeah? Yeah, everything happens on sigma tilde. So the balls are on sigma tilde, the annuli are on. Once you get here, you apply the stability inequality on sigma tilde. What's that? Well, I claim they are because what's that? No, it's trivial because you can just take so there's I guess this was a problem in some problem set, but I understand that there were quite many, so let me just recall it. So the point is that the statement that sigma is stable is logically equivalent to the existence of a positive function, which is, say, a subsolution to the Jacobi operator. And what you can do is that you can just lift that function to sigma tilde and use it as a sufficient criterion to prove stability of sigma tilde. So it's the other implication which is non-trivial, but this one is fine, is smooth. Okay, so now this is what I wanted to tell you about stability. Now, stability is cool, but we also want to go beyond stability. And before doing that, actually, let me open a parenthesis, which on a point which I find extremely fascinating. So this rigidity theorem is interesting, but has quite far-reaching implications. So I claim so let me call, maybe just for brevity. So let me call just Theorem 2 this assertion here. So the assertion that a stable minimal surface in R3 is an affine plane. So the claim is that, in fact, Theorem 2 is logically equivalent to the following assertion, which I would call curvature estimate. So it's the assertion that given any sigma stable minimal in R3, and I'm not saying complete, so it can have a boundary. Like any stable minimal object in R3, then the following estimate is true. So the second fundamental form at any point P times the distance intrinsically on sigma from P to the boundary of sigma is less or equal than a universal constant only depending on R3. And if you remember, well, you will see today in the problem set that somehow bounding the second fundamental form is really like, bounding a second derivative for a graph. That is to say, you get a graphical structure in a neighborhood. And so why is this equivalence true? Well, again, that's one of the problems today. But the idea is that somehow one implication is trivial. So let's say you do gain this curvature estimate. Well, if you have a complete guide and the boundary is at infinity, so you can take this distance as large as you want. So in particular, A must be identically 0 if sigma has no boundary. Therefore, the rigidity is true. And vice versa, so what I wanted to, so somehow this arrow here is trivial, because if the boundary is empty, so if you are in the complete case, then you can pick, morally speaking, you can pick distance to be equal to infinity. This implication here instead, so the fact that the rigidity implies curvature estimate relies on a fundamental idea that has been extremely successful in geometric analysis in the last 20 years, which is the blow-up method. So this is also not just an elliptic method, but is also a method which is very powerful, say, in the study of mean curvature flow. So the idea behind the blow-up method is simply arguing by contradiction. Okay, that's a super powerful idea. So let's say that these estimates were false. So if false, I will not be able to give all the details, but I want to give you the flavor. So if false, you can find a sequence of counterexamples, say sigma I, which I can assume compact, such that this product goes to infinity. So without loss of generality, modulo translating, I can assume that A sigma I at the origin times the distance on sigma I between the origin and the corresponding boundary goes to infinity. And so what I do now is just renormalize. So I can call A sigma I 0. I can call it kappa I. And then I set sigma I tilde to be equal to kappa I times sigma I, where this is just a scaling in R3. And so what happens now is the following, that as I'm, morally speaking, this number is getting very, very large, so I'm multiplying by a large number, I'm dilating the surface. So now so the second fundamental form of sigma I tilde at the origin is equal to 1 for any I. But on the other hand, the boundary is going to infinity, right? So on the other hand, this product is scaling invariant. So the distance on sigma I tilde from the origin to the corresponding dilated boundary is going to infinity. And so what happens? So it's possible to prove, and you will see it today, that sigma I tilde will converge to some sigma tilde infinity, complete, so no boundary, stable, so minimal, with such that A sigma tilde infinity at the origin is equal to 1. But what is the problem? Well, a complete stable minimal surface by the rigidity theorem that we are assuming, because we are now proving this implication here, must be a plane, right? So we constructed a plane whose second fundamental form at the origin is equal to 1. And that's the contradiction. Okay, so now we are okay with stability. Let's talk about positive index. So my favorite question is always the following. So we want to determine the set which I would call P, a subset of the natural numbers, where P is the set of P in N, such that P is the index of a complete embedded minimal surface in R3. So that's the question we were asking yesterday for the tree sphere with a round metric, but we can ask the same question in R3 with a complete metric. And in some sense, this is even harder, we are very, very far from understanding this question, but I wanted to tell you something. So let's look at the following graph. So index 0 is attained, and we have just seen, so this is yes, 0 is attained, and we have in fact just seen that these are only planes, right? How about index 1? Well, the answer is again yes, and I will discuss the same in the immersed category, but now let's focus on the embedded first. So here, we do have some easy examples, namely the catenoids. And there's a theorem by Lopez and Ross, dating back to 1989, which says that these are the only elements having index 1. So if you are a complete minimal surface of index 1, then you are a catenoid, okay? But then how about 2? So 2 turns out to be very hard, and the answer in particular is no. And this was proven by Chodos and Maximo in 2014-15. And the way they proved it is precisely going through an estimate in the spirit of the ones I was discussing at the end of the lecture yesterday. So they proved that the key step, the proof is to prove that the index of a complete minimal surface is bounded by 2/3 the genus plus the number of ends minus 1. And so in particular, if the index were equal to 2, if you had an example with index 2, then the genus plus the number of ends should be less or equal than 9/2, and you reduce the problem to finitely many cases, which understand well, and in particular, you can rule them out. And so how does the table continues? Well, how about 3? So 3 is unknown. How about 4? 4 is also unknown. How about 5? So 5 is yes. So yes, because we do have the so-called Costa-Hoffman mixed surface with genus equal to 1. And so the story could continue. So what is the status in a few words? Well, one can prove that the Costa-Hoffman mix of genus G has index equal to 2G plus 3, which in particular implies that any odd number greater or equal than 5 is attained. There are two outstanding questions in the field, which are whether 3 is attained, which we don't know, and the second one, which is even harder, is whether any even number greater than 2 is attained. And we really don't know the answer to any of these two questions. And actually, something I should tell you is that if you remove the word embedded and you go with immersed, well then there are a lot more examples because there's a strong connection with complex analysis in dimension 1. And in fact, in the immersed category, the answer to each of these questions would be yes. So maybe let me use another color. So if we were enlarging the perspective to immersed, so if we allow for self-intersections, then here the answer is the same. So here the answer would be the same. You only have planes. As far as index 1 is concerned, you would have catenoids, but you also have the n-per surface. And these are the only two. Here the answer would be yes. And there are examples. So for instance, well, I mean, the genus equal 2 cases, I mean, there are examples by Choi, for instance. Here there are various examples, so like the Chen Gachstatter surface or the Richmond surface. And here there are other examples. So the index equal 4 case in the merged category is very interesting. There's, I guess, an example which is due to, well, independently by Kastner and Bryant. So it's an example with 4 ends. And here again you have Kostoff mix plus other examples. Okay, so somehow this is again a very active area of research where we don't really know how to answer most of the questions. And maybe let me finish opening yet another perspective on the same question. So the point is that we asked this question about stable, the presence of stable minimal surfaces in R3, but it's very important in general relativity to ask the same question for asymptotically flat manifolds. So the question will be the following. So what is an asymptotically flat manifold? Well, for the purpose of this talk, it's just a manifold, complete Riemannian manifold, such that if you remove a compact set, you get something that is diffeomorphic to R3 minus a ball. So you may have some topology, but it's confined to a compact set. And in the induced coordinates, we want the metric to be approaching the Euclidean one at infinity. And in particular, I want to assume the following asymptotics here. So I want Gij to be equal to a leading term which is conformally flat, plus some error terms of a higher order, right? And so the way an asymptotically flat looks like is pretty much like this, right? So you may have some topology, but as you go to infinity, you get something that looks like a plane. And this would be the case with one end. So for this object, you can, like I said, you can define an important invariant called ADM mass, which turns out to be actually just equal to this parameter here, as we are assuming sort of special asymptotics. And so the question here one can ask is, what are the stable minimal surfaces in a space like this. So this is just a formal extension of the question in R3. So this is a question which is motivated by somehow the so-called Wisken-Yau foliation. So it's known that outside a compact set you can foliate a manifold like this with large spheres. And this foliation sort of encodes a lot of physics behind these spaces, encodes in particular the Hamiltonian invariant. And so a key question in the field was really to determine whether this foliation was canonical, meaning that the solution to the isoperimetric problem for large volumes were unique. Or more generally, if any large CMC stable sphere were also unique for the volume it encloses. And it turns out that by a blow-up argument, that problem, which is crucial also from a physical perspective, is actually reduced to this geometric question. And so I would like to just mention the conclusion of the story. So of course here we are working in spaces where Euclidean methods don't quite work. We don't have symmetries. We don't have calibrations. So somehow the large-scale structure of this space is very, very far from being Euclidean. And still, one can prove the following result, which is a theorem that I proved in 2014. And this says the following. Let sigma 2 inside M3G as above be a complete, non-compact stable minima surface then the sole assertion that M contains a stable minimal surface determines it completely. So then M3G is R3. So it's isometric to R3 with a flat metric. In particular, it has 0 mass. And sigma is an affine hyperplane, is an affine plane. So this opened the way to the so-called mass detection via submanifolds. And it was really the key to prove what we later did in a paper with Chodosh and Eichmer. This was the key point in going to effective versions of the positive mass theorem. Okay, so I guess I did what I had to do, and it was a great pleasure. Thank you very much. Well, I guess in the index 1 case, it's actually known, I guess the only ones are the Catenoid and N per surface without orientability assumption. But in general, if you allow for non-orientability, then you will have a longer list. So there are definitely more examples than this. I think it's part of the theorem by Lopez and Ross, but I should double check. I mean, it's sort of a subtle point.
For the last theorem, should it be error minimizing or stable minimal? Because I think if...
Sorry,
For the last theorem...
Yes?
2014, it should be error minimizing, complete and non-compact. I think in your paper with Zurich Sean, you have constructed...
Yeah, I do know, but the point here is that I'm assuming asymptotically Schwarzschildian asymptotics. Okay, so the statement, okay, is referred to the setting above. Okay.
That's for example.